Hello, Professor Simmons here. I'm going to review with you how to integrate the length of a curve and how that relates to a notion of projection that we will find useful later in the class. So we'll look at integrating the length of a curve that I've sketched here, going from point A to point B. And we start by breaking the curve into infinitesimal segments ds, as indicated here on the sketch. We find the length literally by adding up all of those segments from A to B. There are two ways to think about this. In Cartesian notation, we might think of ds as having x and y components and use the Pythagorean theorem to relate the square of the length of ds to the x and the y lengths. So then, finding the length of the entire curve is adding up these square root of dx squared plus dy squared along the length indicated. But that looks silly. We should pull out a factor, say, of dx to have an explicit variable that we are integrating over in our one-dimensional integral. That leaves behind a square root of 1 plus dy dx squared. And that's an integral we can do. But in angular notation, we might notice that ds could be projected down onto the x-axis by angle theta. And then we would say that ds was in fact dx secant theta, so that our length integral is adding up secant theta dx from A to B. Now these numerically will give the same answer because cosine theta is dx over ds, meaning dx over dx squared plus dy squared square rooted. So secant theta is literally the same factor that we saw in our original integral. However, the angular notation, as I mentioned, shows that we are projecting ds down onto the x-axis and then integrating along the x-axis. Now, we'll look at a specific example on the next slide. Let's do an example. Of course, there are others in the book. What we will do is find the length of the curve described by y equals x squared from x equals 0 to x equals 1. So we set up our integral with the integrated limits, and here's the form of our integrand. This time, since we have a specific expression for y, we can calculate that y prime is 2x, the square of that is 4x squared, and now we have a specific integrand, and we can actually do the integral. If you're old-fashioned, you might use integral tables or tricks. If you prefer, you might use Mathematica or numerical integration. Either way, you'll find that the answer is about 1.5.